Hi everyone, in this video we're looking at the central limit theorem. So this pertains to the sampling distribution of means. If you haven't already watched the video about sampling distributions, I will link it in the description below. I just want to do a really brief review of what a sampling distribution is. So this is the probability distribution of a sample statistic, and in this video we're specifically talking about the sampling distribution of sample means, because that is what the central limit theorem addresses. So we're imagining we have some kind of population, and from that population we're selecting samples, many samples over and over and over, and measuring the sample mean from each of those. And what we get is this distribution of values that demonstrate what those sample means will be sort of on average, and how much variation there'll be within them. To get a quick visual of this, I'm going to use this Statlet website, statlet.com/sampdist.html. This is the same website I used in the other video, just to get a visual of what we're looking at here. So here is our general population. In this case, we're looking at a skew right population, but it actually doesn't matter what shape the distribution is when we're talking about the central limit theorem. But from our population, we're going to select different samples. Here I'm going to select, here I have one random sample with size 50. So all of these dots in this little dot plot are representing 50 values from our general population. And we're recording the sample mean from this sample. So this particular sample has a mean of 2.91. And I'm plotting that on a dot plot down here for the sampling distribution. So we can do another sample, and we'll get another sample mean. This one's almost the same as the first one. Another one, another one, another one, another one. And we'll see that these sample means vary. So I'm getting, 2.7, 2.7, 3.0, 2.6, 3.3, right? Each sample is going to have slightly different means. But if I make more and more and more and more sample selections, this sampling distribution is showing me how those sample values, those sample means are distributed. I'm going to do 1,000 samples here so we get a nice full dot plot. And you'll see that we have this kind of bell-shaped or a single peak distribution in our dot plot. The peak is at about 3. Down below it says that the mean of this distribution is 2.998. That is almost exactly the same as the population mean, which is not a coincidence. And then we can also see sort of the general shape of this distribution and how spread out it is. So this particular one, pretty much all of the sample means are between 2 and 4, with maybe a couple of exceptions. And we have that strong peak in the middle. This is also demonstrating the standard deviation of those sample means. So this is an example of a sampling distribution curve, or a sampling distribution dot plot in this case, with these 1,000+ randomly generated sample means. So what the central limit theorem says is that if we consider all random samples of a particular size n from a population, and I can't actually generate all the possible samples with that computer program, unless your population is really small, you usually can't actually generate them all. But if we were able to look at all possible random samples from a population and look at the sampling distribution from all of those means from the samples, what we'll find is that this distribution is normal, as long as our sample size is big enough. The mean of the sampling distribution, so the mean of all the sample means, that would be the center of that peak of the sample mean distribution, will match mu, which is our population mean. So that was in the demonstration here that the mean of these sample means was 2.998 and the population mean was actually 3. If we were able to get every possible sample, the mean that we see down here would actually be exactly 3. And the standard deviation of the sampling distribution, which we call standard error, the symbol for this is sigma sub x bar. So this is the standard deviation of the sample mean distribution. That is the standard deviation of this little dot plot in our simulation. That standard deviation is going to follow this formula, sigma over root n, or square root of n. Sigma is the original standard deviation of the population, and the n is the size of the sample. Now, in this statement, I said that the distribution will be normal for large enough n. If your sample size is small, and especially if your population is really far from normal, these distributions might not quite be normal, but the bigger the sample size is, the more sort of perfectly normal the distribution will be. Often you'll see the central limit theorem stated with a criteria that n has to be greater than 30. This is a good kind of rule of thumb for what's a good size sample versus what's too small of a sample. The larger n is, the more perfect the distribution fit is. This sample size is more important for kind of odd populations. If your population is pretty much a normal distribution already, you can still use the central limit theorem properties for small samples as well. And here's sort of a graphical demonstration of the central limit theorem. So I generated this in Python. I created a theoretical population with mean 5 and standard deviation 2. And then from that population, I had the Python program select 30,000 samples, all with size 30, and calculate the sample mean from each of those. So we're looking at a histogram. The horizontal axis here are the sample means. So this is the X bar values. We see values from about 4 to about 6. There's some values above and below that, but that's where most of our bars are located. And there's a obvious central peak right in the middle, about 5, and the heights of all these bars represent the density, or in this case, this is sort of the normalized frequency, so that the area of all of these bars is 1. The vertical axis here is not super important. You can think of it as frequency, although the labels are not counts. So we have this nice bell curved shaped histogram with a peak in the middle, and then there's a red normal distribution line superimposed here. So this solid red line going along the edge of the histogram. This is actually the normal distribution overlaid with these parameters here, where the mean of this normal distribution is 5, and the standard deviation of this normal distribution is calculated using that formula we saw on the previous slide, sigma divided by root n. In this case, sigma was 2. That was the standard deviation from my original population. And the sample size was 30, so n is 30. So 2 divided by root 30 is about 0.37. And that is fitting that red normal distribution curve. So you can see that the red curve it fits pretty nicely with the blue histogram. It's not perfect because these are just random samples, so there's going to be some random noise in the data. But we can definitely see that the mean of these sample means, the mu sub x bar, does match the population mean. And the standard deviation of all of the sample means, while we can't immediately see that on the graph, it does match a standard deviation of sigma over root n when we kind of compare it to that normal distribution. Here's an example where we'll actually use some calculations that involve the central limit theorem. So suppose a chocolate factory produces chocolate bars and packs them into boxes of 20. Over time, they've seen that the individual bars have mean weight 100 grams and standard deviation 15 grams. So I'm thinking of the chocolate bars, the individual chocolate bars, as being kind of the population here. So what they're describing is the mean and the standard deviation of the population. So just to write myself some notes, I'm looking at a population that has a mean of 100 and a standard deviation of 15. The units here are grams because we're talking about weights. The next part of my problem says the quality control manager determines that any box that weighs less than 1,920 grams, which is equivalent to an average of 96 grams per bar, that's just the 1920 divided by 20 bars, is suspicious and potentially underfilled. So the quality control manager is kind of setting this limit at of what an underfilled box might be. So here's the first question I'm going to ask about this scenario. Assuming that chocolate bar weights are roughly normally distributed, what is the probability that a single bar weighs less than 96 grams? So 96 grams was that weight per bar that they set as underfilled. So this question is not a central limit theorem question. This is just talking about an individual chocolate bar from the population of all possible chocolate bars, which we're assuming is a normal distribution. Here's my wonky normal curve here. And we know that the mean of this normal distribution was the mean of those chocolate bar weights. That was mu, or 100 grams. And then the standard deviation was the standard deviation of the chocolate bar weights, which was 15 grams. So the mu and the sigma were given previously. And we want to know what's the probability that a single bar weighs less than 96 grams. 96 grams would be somewhere to the left of the mean because the mean is 100. And I want to know what is the area to the left of 96. So this is just a standard kind of normal distribution question that you would have seen in the previous chapter. I'm going to solve this with Excel, but there are various ways that you could calculate this. So if I have a mean of 100, a standard deviation 15, and we want to know the probability of getting something less than 96, this would be equals norm.dist 96, comma, I'm going to use my mean of 100 and my standard deviation of 15, and this is a cumulative calculation. So I'm putting true in the last input, and I get 0.25249, so about 25%. Quick editor's note, I made a typo in that formula. I put in 90 instead of 96. So the area to the left of 96 with the norm.dist function should actually be 0.3948 or 0.39. So in the rest of the video, I'm saying 25% here, but this should actually be 39%. So there's about a 25% chance that a single bar weighs less than 96 grams. So if I go back to that criteria, the quality control manager is saying that we would consider a box potentially underfilled, maybe it doesn't have enough chocolate bars in it, if it weighs less than 1920, which would be an average of 96 grams per bar. So does that seem like a good criteria if 25% of bars are less than 96 grams? Well, it might immediately seem like, oh, well, that's going to flag lots of boxes. But here we're not saying that any one individual bar in the box is less than 96. We're saying that the average has to be less than 96. So this is where we get to use the central limit theorem. I'm really interested in what is the probability that X bar, a sample mean, is less than 96. So the probability that the mean of a group of 20 randomly selected chocolate bars, what's the probability that that mean is less than 96? So this is going to be my second question. What is the probability that a box weighs less than 1920 or 1920 grams purely due to random chance and not because there's actually fewer than 20 chocolate bars? So here I want to consider the distribution of sample means, which is the sampling distribution. This is, according to the central limit theorem, normal. Now we do want to be a little bit careful here because our sample size is only 20, so we're a little bit on the low side for a sample size. So this calculation may not be exact, but our distribution should be pretty normal. The mean of our sampling distribution is going to match the population mean, which was 100 grams. And finally, the standard deviation of our sample means is going to be the original population standard deviation, which is sigma, divided by the square root of n, or in this case, this would be 15 divided by root 20. This isn't going to be a particularly nice number. I'm just going to kind of leave it as is. So I'm looking at another normal distribution calculation, but it's coming from a different distribution. So this is the sampling distribution. Now the center is going to be the same. It's still going to be 100 because the mean of the sampling distribution is the same as the mean of the wider population of the individual candy bars. But the standard deviation of this sampling distribution of my X bar values is going to be smaller. And 15 divided by root 20 is approximately 3. So we're looking at a distribution that has a standard deviation of 3 rather than a standard deviation of 15. The question I'm asking is still kind of the same. I'm looking at 96 and seeing what is the probability of getting that value or below. But rather than saying what's the probability that a given candy bar is less than 96, I'm asking what's the probability that a sample mean, the mean weight of 20 chocolate bars, is less than 96. So I'm doing the same type of calculation, but my standard deviation is going to be different. This is going to be 15 divided by the square root of 20. In Excel, this would be equals 15 slash SQRT parentheses 20 and parentheses. There's that 3.3-ish number. And I'm going to do my norm.dist function. My x value is 96. My mean is this 100 value. Standard deviation, I'm going to click on the standard deviation I just calculated. If you wanted to, you could actually just type 15 divided by square root of 20 here, and that also works. But since I already calculated this here, I can also click on the cell where that standard deviation is located. And then I'm putting true in for my last input. And this gives me 0.11652. So the probability of this happening is about 11%. This is definitely less than what we saw for an individual chocolate bar, although this is still a fairly high percent. We probably wouldn't want to flag 11% of all the boxes. So it could be that the quality control manager has set a limit that's a little bit too high. If we wanted to, we could ask, how could we set this limit so that we're only checking maybe the lowest 1% or something like that? This is similar to other normal calculations that you might have done in the past section, but just using this sampling distribution. So I could say the lowest 1% of boxes. So that sample mean would be norm.inverse or norm.inv. We would put the lowest 0.01 as our first input. The mean is this 100, and the standard deviation was that computed value of 15 over root 20. And this tells me 92.1972. So maybe an average of 92 grams or less would be more appropriate. Or if we did 92 times 20, that would be a total weight of 1,840 grams. Maybe that might be a more reasonable cutoff. So just to reiterate, we're doing very similar calculations between question 1 and question 2. The difference being question 1 is asking about an individual from the population, and question 2 is looking at a sample mean of these samples of size 20. That is it for this video. Thank you for watching.